Hello, everyone. This is Math 1055 live Q&A number 7, I think. I hope you are all well and safe. Let's jump right in. If you have any questions, use the chat as usual. Let's go to itempool.com/math1055/live and start with this question. So is the infinite series, which is the sum of sine squared of n times pi over 6, with n going from 0 to infinity, convergent? Okay, so we have two choices. It can be convergent or divergent. So is it convergent? We are summing sine squared of n pi over 6. Okay, so just think about the different sort of conditions, criteria that we need for a series to converge, and whether they are met in this for this series. So it's just a warm-up question. Don't worry if you don't get it right. I'm just curious to see what people think. So please don't give away the answer until I finish the poll. In the meantime, if you have questions, if you have answered the question and you have questions related to anything Math 1055, just feel free to ask. Okay, so just for those who have arrived in the last few minutes, just head over to itempool.com/math1055/live and answer this question. Is this infinite series convergent? We are summing the sine squared of n pi over 6 with n going from 0 to infinity. Okay, there are already 59 answers, 60 answers. So feel free to click the link in the chat or just type the link in your browser and head over to itempool.com. Okay, so just let me just point out that we are summing non-negative numbers because we are taking the sine of some of angles and then we square these numbers. So we definitely are dealing with non-negative numbers. So you just have to think what are the necessary conditions for a sum of non-negative numbers to converge. Okay, so these are of course very special numbers because the multiples of pi over 6 are kind of special angles for the sine and the trigonometric functions. So their values are well known exactly. Okay, so there are close to 70 answers, which means 40 of you still haven't voted. That's fine if you don't want to be part of this experiment, this running experiment. Maybe, yeah, I will close this one. I have given you enough time, I think, to vote. And don't worry if you didn't get the chance to vote. You will have plenty of other opportunities. Okay, so yes, the answer was no. It is divergent. Could anyone tell me in the chat why is this series divergent? Succinctly, so just very shortly, like why is it divergent? Any hints? Okay, so there are several answers. So values from 0 to 1 added up is one comment. Yeah, I don't know what you mean by that. If we are adding up values between 0 and 1, not just zeros and ones, but between 0 and 1, we still can get something that is convergent. Think of the reciprocals of powers of 2. So that doesn't tell us anything. It can be 0 or 1. That's kind of closer to what I was thinking. All positive numbers, again, just because we are adding up positive numbers, it doesn't mean it's going to diverge. Think of 1 over 2 to the n. Sums to, strictly increasing is infinite sum of positive numbers will always increase. That is true, but it still could converge. I mean, right? I mean, again, just think of geometric series. It's the partial sums are always increasing, but still they converge to some numbers for geometric series, with quotient being between -1 and, well, 0 and 1. Okay. Fails the ratio test. Yes, well, actually it fails. It does fail not just the ratio test, but it fails a much simpler test, which is the vanishing test. Okay, just remember, yes, sine squared of x diverges. Very, very good. It's not converging anyway. Adam has given us a very precise statement, basically saying that if you are looking at numbers of the form 6k plus 3, you will get basically multiples. You will get something like the sine of pi over 2 or the sine of minus pi over 2 squared. So basically you are squaring plus or minus 1, and you are adding up ones. The point is that this infinite series fails the vanishing test. Okay, so it fails the vanishing test. Yes, Georgia just said the same thing. So if you look at a series and the general terms don't go to 0, don't converge to 0, then it immediately fails the vanishing test, and it means that it's going to diverge. It's going to be divergent. Okay, because if the numbers don't go to 0, you are adding up numbers that are around some non-zero, that tend to some non-zero numbers. You are adding up more and more of those numbers. Or if it's just divergent like this one, again, in this series, you will have +1 included infinitely many times. Okay, so that's the point. It fails the vanishing test. The general term doesn't converge to 0, so it's divergent. But let me just quickly make an important comment. So just because it passes the vanishing test, it doesn't mean automatically that it's going to converge. Think of the harmonic series, 1 over k summed. 1 over k goes to 0, but still the sum, the harmonic series, is divergent. Okay, so just because it passes the vanishing test, it doesn't mean it's going to converge. The vanishing test can be used to establish divergence. If it fails the vanishing test, it's divergent. Okay, I hope that was all clear. Let's go to the next problem. Let me begin accepting answers. And yes, so is this infinite series convergent? And I gave you a hint. I told you to apply the ratio test. So we have k factorial divided by the kth power of k. Okay, so there are some really quickly fast-growing things in this in the numerator and denominator of these fractions. Yes, thank you, Aaron. So and we are adding these numbers up with k going from 1 to infinity. So again, k factorial divided by k to the power k, with k going from 1 to infinity. And I told you to try to apply the ratio test to establish whether it's convergent or divergent, okay? If you need a reminder, the ratio test is nothing but taking the k plus 1th term divided by the kth term in absolute value, take the limit of that, so that you take the limit of the ratio of the consecutive terms, with the k plus first term being upstairs, and if that limit of ratios is less than 1, then it's convergent. If it's greater than 1, then it's divergent. And if it's equal to 1, well, then the test would be inconclusive. Okay, so that's why we have 3 options. The first one being, yes, it is convergent. The second one, yeah, no, it is divergent. And the third one being the ratio test is inconclusive. Yeah, it says inconclusive. There's a typo, so it should read is inconclusive. Okay, so anyways, it takes some time to calculate this limit in the that's involved in the ratio test. So I will give you a minute or two to do that. Can be a bit tricky, but hopefully you will all get it. Well, most of you will get it right. In the meantime, let me just make some preparations so I explain how this worked. So if the limit is greater than 1, then it fails the ratio test, or it means that it will be divergent. Okay, and if you look at the proof of the ratio test, basically this limit can be used. This is a fixed number if it's greater than 1 or smaller than 1. Either way, we use it to give an upper or lower bound our series in terms of a geometric series with that limit being the quotient, basically. So that's the point. If it's the limit is less than 1, then it is dominated by a geometric series that is convergent. If the limit is greater than 1, then it's greater than a geometric series which is divergent. That's the point, basically. Okay, so let me close the poll because time's up. There are 50 votes, so I will just give you 1 more minute so you can vote if you had made some calculations and didn't have the time to submit your vote. So do it now, please. Okay, I don't see any new submissions. Let me finish and reveal. So yes, it is convergent. Okay, so because this is a bit more tricky to explain, I will go to the notepad view. So this is the limit I was referring to. We are taking the limit of the ratios of the consecutive terms. So AK refers to the kth term of the series, and we notice that we took the modulus, the absolute value of these terms. So a sub k plus 1 is divided by a plus k in absolute value. Well, of course, for this series, each term is positive, so these absolute values can be omitted. And this is how we get this ratio of the k plus first term and the kth term. Notice that we can simplify this first of all by k factorial. So here we have the numbers multiplied from 1 to k plus 1. Here we have the numbers multiplied from 1 to k. So with k factorial, we can basically simplify, leaving us with k plus 1 upstairs. We can then simplify by k plus 1, at least one of them. Okay, that's why we have this expression. So what we are left with is this limit as k goes to infinity of k to the power k divided by k plus 1 to the power k. Okay, well, let me write this instead. So I did take k to the power k upstairs, which is the way you divide two fractions, but actually I didn't want to do that, so let me just do it. Let me just not do that. So I will just leave k to the power k over there, where it was. And then in the denominator, we can rearrange this, well, do a bit of manipulation. So instead of taking the kth power of these two numbers, we'll just take, and then take the ratio, then take the fraction. We'll just take k plus 1 divided by k and raise that to the kth power. Okay, so that's all I did in this step. And then, of course, this can be written as the limit as k goes to infinity of 1 divided by, well, this is just, if I divide by k each term, this is just 1 k over k plus 1 over k to the power k. And you might remember that in the denominator, what we have is a famous sequence of numbers, which as k goes to infinity, converges to Euler's number E. So this is the reciprocal of that limit. So this is 1 over E. Okay, so we started with this limit that we wanted to calculate, and we have found that this is 1 over E. Now remember that E is 2.718, so it's greater than 2, greater than 1. That is only the thing that is important, because then 1 over E is strictly less than 1. Okay, so the series is convergent by the ratio test. So was that clear? Was that okay? I hope it was. Again, all I did was apply the ratio test, and after some simplification of terms, yes, let me just quickly say how I cancel these terms. Here we have k factorial, here we had k plus 1 factorial. So the numbers multiplied from 1 to k appears in both of these expressions, but actually if I simplify with all those numbers, here is k plus 1 left upstairs, okay? And then I could simplify with even that k plus 1 by crossing off one of these k plus 1 many k plus 1s in this denominator, okay? And then I was left with k to the power, well, actually I was left with 1 divided by k plus 1 to the power k divided by k to the power k. That was simply rearranged to be like this, and we noticed that this is just a famous limit for Euler's number. Well, this one is the reciprocal of Euler's number. So the ratio test gives us this limit to that it is less than 1, strictly less than 1. So the series is convergent. I hope that was okay. All right, let's move on to the next. Yes, okay. So here is the next question. So Joseph, yes, if you get k to the power k divided by k plus 1 to the power k, that's the same thing. So let me just point out these two expressions here are the same exact thing, right? Because I can always take this k to the power k downstairs like this. Okay. I hope that's fine. You could always, yeah, rearrange it like this. So a over b is the same thing as 1 over b over a. It's just the reciprocal of a fraction. Okay, so here's this question. Is this infinite series absolutely convergent? So here is the notion of absolute convergence. It makes a debut in our live Q&A. So far we've only dealt with convergence of series. Now this is about absolute convergence, and remember, absolute convergence means is something stronger than convergence, is a stronger notion, because it requires the series to be not just convergent, but absolutely convergent in the sense that if you take the absolute value of each term in the series, that series will still be convergent. Okay, there's another question related to the previous problem. So yes, so just because you have a fraction where the denominator is greater than the numerator for all k, for all terms, it doesn't mean that the limit will be less than 1, right? I mean, consider the simpler sequence that is just a sequence of natural numbers. There you would have k over k plus 1. It's always less than 1, but the limit is equal to 1. So getting back to this infinite series, you should take the absolute value of each term. You can notice that there is this minus 1 to the power k plus 1. So there's this sign that is going to alternate for this series. So you will have plus and minus alternating. I'm asking whether it's absolutely convergent. You should take the absolute value of each term, so they are all non-negative, and see whether that series is convergent, because then that means that this sequence, the original sequence that we care about, this one, would be absolutely convergent. Okay, and I gave you the hint to try and compare it to some simpler series, just like we did last week, where we took complicated looking series, looked at the general term, tried to guess how it behaves for large k, for large indices, and then we were able to guess the convergence and then make it rigorous. Okay, there are like 50 something votes. So if you want to vote, you still can go to itempool.com/math1055/live. So go to this this address. There is the link in the chat, and you can hopefully participate in these questions. So I didn't say, but of course we have three now. We have three options. It is possible that this series is absolutely convergent. It is also possible that it is not absolutely convergent. So if you take the absolute value of each term and form that new series of non-negative numbers, then that series would diverge. But this one here would still be convergent. Okay, so it is possible for a series to be convergent with having alternating signs for each term, but the absolute value of each term would add up to infinity. Now, of course, the third possibility is that it's divergent. Okay, I will give you a minute or two just to make sure you can finish your calculations. Again, the general idea is to take the absolute value of each term, the modulus of each term, and try to guess how it behaves for large k, and compare it to a series that we already know to be convergent or divergent. If you think it's convergent, you should compare it to a convergent series by having it being an upper bound, the convergent series, to this one. If you think it's divergent, you should have the divergent series be less than sort of the partial sums of the divergent series being less than the partial sums of this one. Okay, so that's how you compare partial sums and series. All right, so I see something like 70 votes. I guess that's what we have to work with. Let's see. Let me just finish the poll. So yes, the answer was yes, it is absolutely convergent. Again, it's a bit tricky to write it down in the chat, so I'm not going to ask you to do that. Let me just quickly go and say that the general term in this sequence, AK, was -1 to the power k plus 1 times, I think, k minus 2 divided by k cubed plus 1. Okay, and we take the absolute value of each of these terms. In this case, well, this means that taking the absolute value of k minus 2 divided by k cubed plus 1, basically. So getting rid of this alternating sign, and also since k was starting at 1, this number could be negative, but of course at some point k minus 2 is going to be positive and stay positive. So basically from k equals 3 onwards. Okay, so anyways, the point is that this expression for large k behaves something like k divided by k cubed. Okay, because for really large values of k, imagine k being 1,000,000 or something, subtracting 2 or adding 1 to its cube does practically nothing to the number. So it behaves like 1 over k squared. So that's the point. So we expect the sum of AK absolute value to be convergent. So the reason being that the sum of the squares, the reciprocals of squares, is convergent. Okay, it's pi squared over 6, but that doesn't. All you have to know is it's convergent, and in fact we can say that this absolute value of each term summed up, which is again these numbers summed from k to infinity, k equals to 1 to infinity, is strictly less. Each term is strictly less than the sum of k divided by k cubed. In fact, it's strictly less because we increase the numerator by 2 and decrease the denominator by 1, so we are getting strictly greater fractions this way. Okay, and this is just the sum of the reciprocals of squares, and this is convergent. Okay, so we have a series that is convergent being greater than the series that we are interested in, which was the sum of absolute values of the terms in the original sequence. So this series is convergent, meaning that the original series is absolutely convergent. So that's where the name comes from. Okay, I hope that was clear. Feel free to ask questions if anything was unclear, or if you want something to be repeated, maybe in a different way. But in the meantime, here is the next question. Again, we have an alternating series, but I'm asking you to apply the alternating series test in this case, and decide whether it's convergent, divergent, or maybe the alternating series test does not give you an answer. So yes, Christopher asked me to go back to the working out. Yes. So do you have any specific questions? Because I'm happy to go back to the previous problem if you have a specific question. So Alexander is asking, could you use the ratio test and then say if it is convergent by the ratio test, and then it is convergent by definition? Do you mean this question right here? For this question, could we use the ratio test? The question before. So for the question before, the ratio test wouldn't give you anything. It would actually, so the limit of these ratios would be equal to 1, in which case the ratio test doesn't tell you anything. Okay, so in this question, I'm asking you to specifically apply the alternating series test to this infinite series of -1 to the power k times 1 plus the cosine of k times pi, whole thing divided by k, with k going from 1 to infinity. Christopher, in the meantime, do you have your question about the previous working out? I mean, I can still go back to that screen and again quickly tell you what we did. We took the absolute value of each term. That is how it looks like. And then we just gave it an upper estimate by increasing the the numerator and decreasing the denominator. So we are dividing larger numbers by smaller numbers, resulting in a strictly greater number for each term. And k divided by k cubed is 1 over k squared. And that infinite series we know to be convergent, and it's strictly greater. So the sum of these non-negative numbers have to converge. Okay, cool. So we don't, yeah. So I guess I clarified that. Good. Okay, so let's get back to this question then. Here we have again something that we've seen before. We take the cosine of multiples of pi. Okay, just so that's a crucial point in this question to realize that here we are just taking multiples of pi, integer multiples of pi, and then take the cosine of those angles, and they are very special indeed. So if you remember the cosine function, it behaves very nicely in general, but the values it takes at multiples of pi are very nice indeed. Okay, so yes, the alternating series test. I should, of course, remind you what that is. So it consists of two parts, the alternating series test. First of all, the alternating series test includes the vanishing test within it. So first, you should check whether the vanishing test fails. So whether the series fails the vanishing test or not. If it passes the vanishing test, that's an indication that it could converge. So that the series, then you should move on to step 2 in the alternating series test, which is nothing but looking at the absolute value of each term. So without this alternating part of -1 to the power k, and see whether the non-negative part of each term is strictly decreasing as k increases. Okay, so passing the vanishing test and having strictly decreasing terms in absolute value is the two things that you need for the alternating series test to be passed. And if an alternating series passes the alternating series test, it means it's convergent. So that is a proposition we had, or theorem we had in the lectures. Passing the alternating series test implies convergence. Okay, so there are 67 votes at the moment. I'll give you another minute or two to think about this. It's not too difficult. Again, two things you have to check. First thing, does the general term vanish, go to 0 in the limit as k goes to infinity? And do the terms form a decreasing sequence, a strictly decreasing sequence in absolute value? When you take the absolute value of each term, do they form a strictly decreasing sequence? Both of these things have to be satisfied in order to get a convergent series. Now, again, there is this typo. The alternating series test could be inconclusive. So the third option is the alternating series test is inconclusive. Okay, so let me close this poll. finish this for this question. Okay, so this is very interesting. This is very interesting. So what we have here, is a series for which the alternating series test is inconclusive. Okay, so let me show you why it is inconclusive. So first of all, it passes the vanishing test. So there's no problem there. Let me just write down the general term. So here we have 1 plus the cosine of k times pi divided by k. Okay, so this is ak. Of course, there is this sign alternating in front, but we are more interested in these non-negative numbers. So taking the absolute value of each term. So first of all, what we should notice is that the cosine of multiples of pi is either +1 or -1. Okay. Now that I got this help from Professor Mikhailov saying that it's not actually an alternating series, which is true, I guess. We'll see. Okay, anyways, let me just go through because let me think. Okay, I could potentially modify it to be 1. Anyways, the point is, let me just go through the calculation anyway. So it's 1 plus, what we have here is -1 to the power k. Okay, so the cosine of k times pi is +1 if k is an even number and -1 if k is an odd number. Just think of the cosine of 0 is 1, the cosine of pi is -1, and then this keeps happening for even multiples of pi, you get +1. For odd multiples of pi, you get -1. So this is what we have here, divided by k. So we have two possibilities. If k is even, that means we have 1 plus 1 in the numerator divided by k. So that's 2 over k. If k is even, k even. Okay. And if we have odd k's, we have 1 minus 1, giving us 0. So this is indeed the problem, what the professor was telling me, that indeed we don't have alternating terms really. It just looks like an alternating series, but in reality it doesn't have negative terms, so it's just a fake alternating series. Now, anyways, the point is that what we have here, let me go and just finish this anyway. So this was the original series, and if it was an alternating series, the alternating series test would be inconclusive. So the point is that the vanishing test is passed because these numbers in fact converge to 0 as k goes to infinity, but they are not, they don't form a strictly decreasing sequence. Okay, so that was kind of the point. So if k is even, and there is a better example. I will post that after the lecture. So if k is even, k is of the form of 2m, then what we have here is the sum with m going from 1 to infinity of 1 over m. Okay, so in fact this series is just the harmonic series in disguise. Anyways, let's move on to the next one. Let me look at the questions. So I don't see any good. Okay. Yes. So there is this example. The professor was kind enough to to give me this example. So you can all check how this sequence behaves. So all we did was write 2 instead of 1 upstairs. Okay. So let me go back to the chat. So what is the general rule for being inconclusive? Okay, let me just tell you then what I meant by this question. So the point is that the alternating series test can only tell you if a series is convergent. So it only works in that way. So it's almost almost works the opposite way than our vanishing test. First of all, you apply the vanishing test, so you check whether it could converge, and then you have this strictly decreasing sequences of numbers when you take the absolute value of each term. And if they don't strictly decrease, the series could still converge or diverge, and the alternating series test doesn't tell you anything more. Okay, so that's the point. The alternating series test, if it is passed by the series, then it means it's convergent. But if the alternating series test is failed by the series, then we are left with we are back to square one, so to speak. Okay. Yes, so basically that factor of -1 to the power k doesn't really do anything because it's just alternating between +1 and -1, so it's just really just a sign. So whether you include it or not, it doesn't affect the general term converging to 0. Okay. So if it converges to 0 and you multiply it with -1 to the power k, it will still converge to 0. Okay. Shall we move on to the next question then? So this is the last question for today. What is the radius of convergence for the following power series? And then we have this alternating series, but it is a power series, which means it includes powers of x, and sort of a variable or indeterminate. X can take basically any real value, and indeed our job here, and usually with power series, is to see for which values of x will it actually give you something that's sensible. Okay, so there is this infinite sum, and it could happen that for some values of x it gives you infinity, so it doesn't make sense, it diverges to infinity. But for other values of x, it could give you a sensible finite answer. So the sum could be a finite number, and this radius of convergence gives you an interval on the real line within which you can pick x's so that the sum makes sense, converges. Okay, and for the radius of convergence, we have this definition. So if you write the power series in this general form, which is the sum of c sub k times x to the power k, and then you form the limit of the ratio of absolute values of ck and ck plus 1. So notice that we have ck upstairs and ck plus 1 downstairs, and we take this limit. If it exists, and if it's a finite number, then that is our radius of convergence. Okay, it's should be fairly easy. All you have to do is use the definition and calculate a simple limit. Notice and don't forget to take the absolute value of each term. So here we have -1 to the power k plus 1 times x to the power k divided by k. And I spelled it out, so I've written the first few terms of this infinite series, this power series. It starts with x, then it has x squared over 2 subtracted, then we add x cubed over 3, subtract x to the 4 divided by 4, and so on. So the signs are alternating, and we have larger and larger powers of x divided by actually the exponent. Okay, so in the lectures we have seen that the power series of the exponential function x to the power k divided by k factorial, with k going from 0 to infinity, has an infinite radius of convergence, which means that this limit diverges to plus infinity, and that means that for all real numbers, the entire number line is good for us to pick our x, and the infinite series, the power series, makes sense, produces this exponential function. But this is not the power series for the exponential function. This is actually a power series for some other function, but I didn't tell you which function it is. I will tell you once we are done. So some of you have voted. I hope it was not too difficult. Let me reveal the answer because we are running out of time, and quickly show you what the radius of convergence was. Yeah, so it's +1. It cannot be a negative number because we are taking the limit of non-negative numbers. Notice taking the absolute values. So just quickly, let me just quickly show you that what we did is we basically took 1 over k divided by 1 over k plus 1. No, sorry. How did we? Yes, this was it. So that's ck divided by ck plus 1. And then we take the limit. Well, let me just rewrite this as k plus 1 over k. And if you take the limit as k goes to infinity, this is just 1 plus 1. As k goes to infinity. Okay, so this number r is equal to 1 is the radius of convergence. Okay, which means that this power series, k going from 1 to infinity, -1 to the power k times x to the power k divided by k, gives rise to something sensible for x being between -1 and +1. And in fact, the sum, well, you might not guess this, is the natural logarithm of x plus 1. Okay, so it's the natural log of x plus 1. So this is the so-called Taylor series of the logarithm function. And in fact, this radius of convergence is equal to 1. We should check what happens at the end points. So what if x is equal to -1? Well, if we look at this series and we put x equals -1, we would get what do we get? So that's not that doesn't look good. Might have got it a bit wrong. Yes, then we get the harmonic series. Okay, so if x is equal to -1, then we get minus the harmonic series, giving us -infinity. So it diverges to -infinity at x equals 1 diverges to minus infinity, which kind of makes sense because if x goes to -1, then we go to the logarithm of 0, and remember that the log function looks like something like this. It goes to minus infinity as x goes to 0. It's 0 at x equals 1. Well, this is not correct. Should call this capital X. So if the argument is equal to 1, so little x is equal to 0, then we get 0, of course, because we are adding zeros. And if x is equal to 1 plus 1, what do we get here? We get an alternating series. We get actually the alternating harmonic series. So 1 minus a half plus a third minus a fourth and so on, which is convergent by the alternating series test. So indeed, x equals plus 1 is included in the so it gives rise to a sensible number, and in fact then we would get log 2. So the alternating harmonic series gives us log 2. So this is just for fun, I'm mentioning that this infinite series will give you log 2. Okay, so let me stop here. Thank you very much for your attention, and I'll see you next week. Have a good weekend, everyone. Yeah, there was this question. The point is that we are taking the absolute value of each term, so this -1 to the power k doesn't matter. Okay, thank you, everyone. Hope you enjoyed it.